Naming enantiomers continue. If instead of perspective drawings, we have Fisher projections, the rules for determining whether the molecule is R or S are different. This is going to depend on whether the position of the lowest priority group is on a vertical bond or a horizontal bond. So, beginning with the lowest priority group on a vertical bond. If the lowest priority group is on a vertical bond, then clockwise is R and counterclockwise is S. Clockwise is R, counterclockwise is S. This is because the vertical bonds are hatched wedges. So we can number the priority groups and ignore all groups except for 1, 2, and 3. So we ignore group 4, but we still need to know where it is located, so we still give it a number. When we draw the arrows, we draw them from 1 to 2, and then from 2 to 3 without passing 1. You can pass group 4 on the way to group 3, but you cannot pass group 1 on the way to group 3. Looking at the enantiomer at the right, the S3-chlorohexane, we have the groups chlorine at the top, propyl at the left, and ethyl at the right. As we go from 1 to 2 and from 2 to 3, we are moving counterclockwise, and that gives us the S for our naming. Okay, looking at the next rule. If the lowest priority group is on a horizontal bond, then counterclockwise is R and clockwise is S. Notice that it flips. If the lowest priority group is on a horizontal bond, it's on a wedge that is coming towards you. Then counterclockwise is R and clockwise is S. If I were writing this on a test, I would write at the top of my test before I started, V, standing for vertical, arrow showing counterclockwise direction with an S, arrow showing clockwise direction with an S. Then I would write H, standing for horizontal, counterclockwise arrow with R, and clockwise arrow with S. And that's how I would keep them distinct. And again, what you do, once you have them labeled as 1, 2, 3, or 4, hydroxyl being 1, ethyl being 2, methyl being 3, you move from 1 to 2 and from 2 to 3, and the direction that it is going is clockwise. And because it's on a horizontal bond, that is the S isomer. Here's a summary. Perspective, H on the hatched wedge. Clockwise is R, counterclockwise is S. Fisher drawing, H is on the vertical. Clockwise is R, counterclockwise is S. Fisher drawing, H is horizontal. Clockwise is S, counterclockwise is R. You will need to know this. It will not be given to you on an exam. The one property which differs from between enantiomers is the direction in which the enantiomer rotates plane polarized light. This is what you did with the Polarimeter lab. What is polarized light? Normal light rays oscillate in all directions. So the light travels in all directions. A polarizer is a lens that orients the light so that it is only traveling in one direction. It is traveling in one plane, and so going through the polarizer, The light is now plain polarized light. An achiral compound cannot cause plain polarized light to rotate. But a chiral compound, as demonstrated by the picture, will take light that is plain and polarized by a polarizing lens, and when that light passes through a liquid sample of the substance, passing through this liquid sample causes the plane of light to rotate. Notice that the arrows are beginning to rotate. When the plane of light comes out the other side, it has been rotated by a specific degree of rotation, and all the light rays are in that degree. We can measure the degree at which the light has rotated. We can also designate isomers as follows. If the enantiomer rotates the plane of light clockwise, it is called positive or dextrorotary, rotating to the right. If the compound rotates the plane counterclockwise, it is called minus or levorotary, to the left. R versus S, and R and S versus positive and minus. These two terms are completely unrelated. They are distinct designations, and some R enantiomers are positive and some R enantiomers are negative. Some S enantiomers are positive and some are negative. We cannot say which is which. For example, S lactic acid rotates light to the right, clockwise. But if we deprotonate the carboxylic acid group to make sodium lactate, the chiral center is still S because the priority of the groups hasn't changed, but now the molecule rotates light counterclockwise. A polarimeter is used to measure the degree of rotation of light. We need temperature, the specific rotation, which is a known value, the wavelength, the observed rotation that you indicate as a measurement of your eye, the length of the sample tube, and the concentration in grams per milliliter, which is the density. So the formula is that you have a specific rotation, and we don't use what we use for the temperature and wavelength for is that this specific rotation is only valid at the temperature and wavelength that you are currently measuring. If you change the wavelength or the temperature, the specific rotation changes. So we don't actually use these numbers, but we say that this specific rotation only occurs at this temperature and this wavelength. Then we can calculate this specific rotation at a specific temperature and wavelength by taking our observed rotation that we see with our eye, the length of the tube, so take specific rotation observed by the eye, divided by the length of the tube, and divided by the concentration. If one enantiomer is clockwise, then the other enantiomer is counterclockwise. If you know one is clockwise, you do not need to measure the other enantiomer. The other nice thing about the enantiomers is that they rotate light in equal but opposite directions. So the specific rotation, for example, of R2-methylbutanol at 20 degrees Celsius, rotating light at the wavelength called D, is positive 5.75 degrees clockwise. Its enantiomer rotates light under the same conditions at negative 5.75 degrees counterclockwise. This is a favorite question on the ACS exam. Every ACS exam I have seen for organic chemistry has one question where it asks, if such and such isomer rotates light at this, how does its enantiomer rotate light? And all you have to do is remember the change in sign. We can use specific rotation to calculate what we call enantiomeric excess, or the excess of one enantiomer in a mixture. Enantiomeric excess is the observed specific rotation divided by the specific rotation of the pure enantiomer times 100%. There are other methods to determine this as well. So here's a problem. If a sample of 2-bromobutane has observed specific rotation of positive 9.2, then the enantiomeric excess is 40%. In other words, the excess of one of the enantiomers comprises 40% of the mixture. So the specific rotation of 2-bromobutane is 9.2, and the specific rotation of the pure enantiomer is 23.1. We don't actually know the value 23.1, but the value 40% we can use to get how much of R and how much of S are actually present. So the math problem that I prefer to do is to say, if I have 40% excess of our clockwise rotating enantiomer, then I can say that I can come up with two formulas, that x minus y is equal to 40%, and that x plus y is equal to 100. What does that mean? The amount of positive rotating isomer must be equal to plus the amount of counterclockwise rotating isomer must equal to 100%. And the difference in the isomers, because one is excess of the other by 40%, must be 40. So we can write the formula that x minus y is equal to the percentage of enantiomeric excess. But x plus y is equal to 100. We can do the math and you will see that 70 plus 30 is equal to 100, but 70 minus 30 is equal to 40. So now I know that my solution is 70% of the positive rotating isomer and 30% of the negative rotating isomer. I can use this information to determine one of the values in this equation.